Welcome to this NPTEL lectures on robotics, basics and advanced concepts. In the last few lectures, we have done the velocity analysis of serial and parallel robots. In this last lecture, we'll look at the statics of serial and parallel manipulators. We will see that there is an intimate connection between the velocity kinematics and the statics. In particular, we'll see that the Jacobian matrix, which appears when we do the velocity kinematics, also appears in the statics of serial and parallel manipulators. So let's continue. This is the last lecture on statics of serial and parallel manipulators. So what do we mean by statics? We basically lock all the joints in a serial robot. And if we lock all the joints in a serial manipulator, the manipulator becomes a structure. So if you have 3 degrees of freedom serial robot, and so there are 3 motors, and if you lock all these 3 motors, then the manipulator will not move. So the forces and moments acting at the joints when the manipulator structure is subjected to external forces and moment is the topic of statics of serial and serial manipulators. The same thing will happen when we look at the statics of parallel manipulators. So basically, we are interested in finding out what is happening at the joints when the manipulator structure is subjected to external forces and moment. Remember, the joints are locked. The actuated joints are locked in a parallel manipulator. Okay. Another problem which we are interested in the statics of serial and parallel manipulator is the following. So let us assume that the manipulator is pushing some object or carrying a payload. Okay. So when it is pushing an object, it is moving very slowly. It is more or less static. Okay. So we would like to know what are the forces and moments which are acting at the joints due to this pushing force which this end effector is applying. Okay. So we want to know what are the forces and torques which need to be applied at the joints such that there is static equilibrium when it is pushing an object or when it is holding on to a payload. And how do we obtain these forces and moments at the joints when there is an external force or a moment acting on the manipulator structure? Basically, we have to use the notion of free body diagram and equations of static equilibrium. So this is a very well-known, well-understood, done in undergraduate many places. So basically what we want to do is we want to draw the free body diagram. So basically the free body diagram of a link will consist of the link, and we show all the external forces and moments which are acting on this link. So this is a link I. The z-axis is along the joint axis. The link I plus 1 is after this joint axis, same as before. There is no change in our convention. So the only thing is the x, y, and z axis and the origin are shown for link I. Similarly, the x, y, and z axis I plus 1 coordinate system and the origin OI plus 1 is shown. There is a vector which locates the I plus 1th origin with respect to the ith origin. So this is this vector I plus 1. Okay, now let's show all the forces and moments which are acting on this link I. So we will denote all the moments which are acting on this link I by Ni. Okay, the symbol Ni, bold-faced Ni. And all the forces which are acting on link I by Fi. Okay, so what is this Ni and Fi when you draw the free body diagram? These are basically the forces and moments acting on link I from the link I minus 1. Okay, this is important. So it is the forces and moments exerted on link I by link I minus 1. Okay, so what is Fi plus 1? It is the force and Ni plus 1. It is the forces and moments acting on link I from link I plus 1. Okay. So for static equilibrium, the sum of all the forces must be equal to 0. So I Fi minus I Fi plus 1. Okay, where is this minus sign coming? Because Fi plus 1 is the force which is acting on the link I plus 1. So the equal and opposite force is acting on link I. Okay, so is that clear? And we are going to do vector summation, so they must be written in the same coordinate system. So we are describing this Fi in the ith coordinate system and Fi plus in the ith coordinate system. So sum of these two forces must be equal to 0. Okay, so as I said, Fi plus 1 is the force on link I plus 1 exerted by link I. Hence, the force on link I exerted by link I plus 1 will be equal and of opposite sign. And the leading superscript I signifies that the vectors are described in I. For static equilibrium, not only the sum of the forces must be equal to 0, the sum of the moments must also be equal to 0. So what is the moment on link I from I minus 1? That is Ni. Ni plus 1 is the moment acting on link I plus 1 from link I. So an equal and opposite moment will act on link I, which is this term. And then we have the R cross F term. So basically a moment generated by this force Fi plus 1 at a distance OI plus 1. Okay, so this is like standard undergraduate statics. So the moment due to a force is R cross that force. Cross means cross product. Okay, so here also we have I plus 1 cross Fi plus 1. This minus sign again comes from the fact that Fi plus 1 is the force acting on link I plus 1. So equal and opposite force is acting on link I. Okay, so again the negative sign is due to the same reason as for forces. So we have these two equations, sum of the forces acting on link I equal to 0 and sum of the moments acting on link I is equal to 0. We can rewrite these two equations in this form. It's a nice iterative form. So IFI was equal to IFI plus 1. Okay, previous IFI is IFI plus 1. Okay, but we can rewrite this by pre-multiplying by a rotation matrix I plus 1 R into I plus 1 Fi plus 1. Okay, so what is this rotation matrix? This is the link I plus 1 with respect to the is coordinate system. Similarly, Ni can be written as I plus 1 rotation matrix into I plus 1 Ni plus 1 plus Oi plus 1 into IFI. Okay, there is a reason why we want to write it in this way, because we will go backwards. Okay, so we will do what is called as an inward recursion for forces and moments on each link. So typically the forces and moments at the end effector, which is the Fn plus 1 link. Remember, the end effector is the after the joined n. Okay, so the force and moment which are acting on the end effector, either in its own coordinate system or in some other coordinate system, is known. Okay, so most of the time, if it is not in contact with the environment, if it is free space, then it is 0. Okay, otherwise, if it is pushing against something or lifting some payload or doing some work, okay, then this force which is acting on the end effector is known. So knowing the force and the moment acting on the end effector, we can substitute on the right hand side and we can find out what is happening to the force and moment in the previous link. And likewise, if I know on the n minus 1th link, I can go back and calculate on the n minus 2th link and so on. Okay, so this is an idea of inward recursion. Remember, in the case of velocity, we went outward. We started from the fixed base and went to the end effector. In the case of forces, we are going backwards. Okay, and it is intuitively correct. In the case of velocities, the base velocity is fixed or 0. Okay, whereas in the case of forces, the external force is acting on the end effector and that is known. So we can recursively compute IFI, INI for I n to 1 using this equation. So the joint can only apply force or moment along the z-axis. We are dealing with 1 degree of freedom rotary or prismatic joints. So a rotary joint can apply a moment about the joint axis. A sliding joint can apply a force along the joint axis. All other components of the force Fi and Ni, which is acting at the joint, are resisted by the structure. Okay, so there are bearings which will take care of radial loads and other kinds of loads. So the torque required to maintain equilibrium at joint I is nothing but the component of the moment along the z-axis if it is a rotary joint, or the component of the force along the z-axis if it is a prismatic joint. Okay, so you can think of that there is an external force acting. How much force or how much torque should I apply at joint I such that the whole structure, whole manipulator remains as a structure? So we know that the motors can only apply along the joint axis or rotate about the joint axis. So hence we can find the Z component of this Ni or the Fi vector. Okay, Fi if it is a prismatic joint, Ni if it was a rotary joint. Example. So let's consider a planar 3R manipulator applying a force to the environment. So the force is Fx Fy0 and it is with respect to the 0th coordinate system. So somehow we have figured out that this planar 3R manipulator is applying a force with components Fx Fy0, 0 because it's in a planar example, and it is with respect to the 0th coordinate system. It is also applying a moment, okay, about the environment. So you can think of it as carrying a wrench and it is trying to tighten a nut, for example. Okay, and again, the moment is only along the z-axis. The x and y components are 0. So first thing to do is we want to convert this force and moment into the tool coordinate system. Okay, because remember, we need I plus 1, Fi plus 1. So we need the force in its own coordinate system, the moment in its own coordinate system. Okay, so how do we do that? Let's call those forces Fx prime, Fy prime, and 0. We have to pre-multiply by a rotation matrix. So instead of writing it in the 0 coordinate system, we can write with respect to tool 0 rotation matrix into this will give me the force in its own coordinate system. That rotation matrix, if you think a little bit, is this. It is nothing but cosine of theta 1 plus theta 2 plus theta 3, sin theta 1, 2, 3, minus sin theta 1, 2, 3, and cos theta 1, 2, 3. And the z-axis is remaining same. The moment in its own coordinate system is a single vector along the z-axis, and it will be the same. Okay, it does not matter whether it is, because only the x and y rotation is about z-axis. So if the moment is already about z-axis, nothing happens. Okay, so I plus 1 Ni for the tool coordinate system is 0, 0, and z. I plus 1 Fi plus 1 for the force in the tool coordinate system is given by Fx prime, Fy prime, 0. Okay, so for I equals 3, okay, we know I plus 1, Fi plus 1, which is Fx prime, Fy prime, 0. So we can compute 3F3. Okay, then for I equals 3, we know what is 3 and 3. How do I find out 3 and 3? That is based on this inward recursion formula. So basically, we can show that it is a moment plus some L3 into Fy prime. Okay, so there is a moment which is acting here, but then it will have some L3, okay, into some Fy prime. Okay, so Fy into L3 will give another moment which is along the z-axis. The Fx into L3 is along the same direction and will not contribute to the moment. So 3 and 3 will be given by this. Then we substitute I equal to in the recursion formula and we can obtain 2F2, and it turns out to be cosine theta 3 Fx prime minus sine theta 3 Fy prime x component, y component is s3 fx prime, c3 fy prime 0, and the moment is nz prime, which was there, then L3 Fy prime, which is there, but then we have an additional component coming from the L because of the moment arm L2. So L2 S3 Fx prime plus L2 C3 Fy prime. Finally, we can substitute I in this equal to 1 in the recursion formula, and we can get 1 F1 and 1 N1. Okay, so 1 F1 is some cosine theta 2 plus theta 3 Fx prime minus sine theta 2 plus theta 3 Fy prime, and so on. Okay, and similarly the moment is nz prime, then L3 Fy prime, then this term, and then one more additional term due to L1. Okay, so and what are now the joint torques which are required to maintain equilibrium? We just take the z component of 1n1 for tau 1, z component of 2n2 for tau 2, and again z component of 3n3 for tau 3. So in this case, we are looking at the moments because all the joints are rotary joints and they can only apply a moment. So if you take the z component, we'll get some nz prime plus fx prime into L1 S23 plus L2 S3 plus Fy prime, L1 C23 plus L2 C3 plus L3. Okay, and so on. Tau 3 will be nz prime plus L3 into Fy prime. So these above equations, these three equations can be rearranged to be written like this. So the left hand side is this vector tau, which is tau 1, tau 2, tau 3. The right hand side is fx, fy, 0, 0, 0, and z. Okay, so we have a force which is acting at that end in the zeroth coordinate system. We have reconverted it back to fx, fy, and z, not primes anymore. Okay, and the left hand side is tau 1, tau 2, tau 3. And this, we have a matrix with elements like this. So the first element is minus L1 S1, minus L2 S12, minus L3 S123, then L1 C1 plus L2 C12 plus L3 C123, and 3 zeros 1. Okay, the last row, for example, is minus L2 S123, L3 C123, 0, 0, 0, 1. So if you look a little bit carefully at this matrix, you can see that you have seen this matrix before. Okay, so if you go back to velocity kinematics, you may recall what is this matrix for the planar 3R manipulator. So it turns out that the terms in the square bracket is nothing but the transpose of the Jacobian matrix. Remember, we had derived the Jacobian matrix using velocity propagation and then again rearranging terms for the planar 3R example. So the term here, what we get is transpose of that Jacobian matrix, which we have already seen. Okay, so this is the interesting part. We are doing statics, but the Jacobian matrix, which we had derived for velocity kinematics, appears. Not exactly the Jacobian matrix, but the transpose of the Jacobian matrix appears. Okay. So as in velocities, we can denote forces and moment acting on the end effector by 6x1 entity, not really a vector. So first, top 3 is the force acting at the end effector, and the bottom 3 are the 3 components of the moment which are acting at the end effector. So basically fx, fy, fz, nx, ny, mz. So this is not really a vector because the force and moment have different units. Okay. So what is force? Newton. What is moment? Newton meter. Okay. So they have different units. This quantity 0f tool is called a wrench in theoretical kinematics. Okay, so basically a wrench can be thought of as a screw with a magnitude which has units of force. Okay, let's not worry about it. But in theoretical kinematics, a combination like this using some nicer approaches like using homogeneous coordinates can be thought as a 6x1 entity, proper entity, without this messing up of units. So now consider an infinitesimal Cartesian displacement of the end effector. Okay, so what do we mean by Cartesian displacement? So there is a displacement of delta x, delta y, delta z, and also let us think of a small change in the orientation given by delta theta. Okay, so a little bit of hand waving, but we know that we can derive the three Euler angles, and then we can think of the change in orientation roughly in terms of delta theta. Okay, so the virtual work done by this tool, by this force and moment which is acting on this end effector. So the virtual work done by the external forces moments can be equated to the virtual work done by at the joints. So what is the virtual work done by the end effector? At the end effector, it is the force and moment dot product with this infinitesimal displacement delta x. Okay, so it is delta f dot delta x, which is nothing but f dot delta x plus moment dot delta theta. Okay, and what is the virtual work done at the joints? It is tau dot delta theta. So from the definition of Jacobian, what is the Jacobian? This is delta x Cartesian displacement is related to j into delta theta. Okay, so it's very similar to velocity is equal to j into theta dot. So now we can say that this force dot delta x is nothing but dot j into delta theta is equal to tau dot delta theta. Okay, so the above equation holds for all delta theta. This is the standard way we use this principle of virtual work, and hence we can show that this tau is nothing but j transpose f tool, because this dot product, okay, a dot b is nothing but j transpose this f. Okay, so if you think a little bit, we can see that this extra torque at the joints is related to the external forces and moments by this j transpose. Okay, and hence it is not very surprising that the Jacobian appears in statics. Okay, so this is a very, very useful expression. It tells you that if you apply a force on the end effector in a serial robot, you need to apply some torque to keep it in equilibrium, and this torque is given by j transpose f. How about parallel manipulator statics? So for serial manipulators, tau is j transpose f. Okay, the principle of virtual work is equally applicable for parallel manipulator. Okay, so all we need to do is we need to say instead of j we have j equivalent. And what was j equivalent? J equivalent had to deal with jv star, k star, k, and so on. Okay, and similarly j omega star, k star, k inverse, and all these various things which we had derived in the velocity analysis. So what is the subtle difference? Basically we have to say that the tool is the chosen end effector. Okay, in a serial manipulator the end effector is very natural. In a parallel manipulator we have to derive this Jacobian for the chosen end effector. Okay, and this j equivalent is the equivalent Jacobian. It is a function of all the passive and active joints. It's a function of the Q's, the configuration variables. And tau is the vector of forces or torque applied at the actuated joints only. Okay, so in a parallel manipulator we have actuated joints and passive joints. You are not going to apply any torque on the passive joints. So tau is only the forces and moments which are applied on the actuated joints. It is quite difficult to compute j equivalent. basically because there is a K star inverse. If you go back and see the notes, you can see that J equivalent in a parallel robot contains this K and K star inverse. The inverse problem is to obtain the forces and moments applied by the tool. Okay, so suppose I give you the joint torques that we are applying so much moment or so much torque at the joints. What is the end effector applying to the environment? So we could symbolically write it as inverse of this matrix, which is what is written here, JQ inverse, or sorry, JQ transpose and the inverse of the whole thing. So that is the force which the end effector is applying onto the environment. So this is clearly very, very hard to obtain. Why? Because J equivalent already had some K in K star inverse. Now you have to find the inverse of that whole quantity. Okay, so this is not possible to do for most parallel robots. However, it is required to be solved for several robots, and it can solve very simply for a Gauss-Stewart platform. Okay, so it can be shown to be very easily solvable for a fully in parallel manipulator, meaning that between the output and the input there is only one actuated joint. So let's go back and look at this in a little bit more detail. So the leg of a Stewart platform consists of one P joint, one S joint at the top platform, moving platform, and a U joint at the base, fixed base. So there is a vector B0 Bi, there is a vector B0 T to the origin of the moving platform. There is a local vector which locates a spherical joint in the moving coordinate system, and then there is this two rotations at this hook joint. Okay, so we can rewrite this vector from Bi to Si. Okay, so basically the vector along the leg is nothing but P0 Pi this plus this minus this vector. Okay, so B0T plus P0 Pi rotated back into the base coordinate system in the B0 coordinate system minus this, so that will give this vector. The unit vector along this leg is nothing but this vector divided by Li, because the magnitude of this vector is the translation at the prismatic joint. So the force exerted by the actuated prismatic joint is nothing but Fi into B0 Si, so along the unit vector. The moment of the force about the origin B0, okay, so the unit vector, there is a force acting this, so the moment will be this vector cross that force, okay, which is what is written here, B0 Bi cross B0 Si into this Fi. So if you denote the external force and moment by F tool, which is nothing but the force acting on the end effector and the moment acting on the end effector, this must be balanced by the force along the leg and the moment which is acting with respect to the fixed coordinate system. So this must be equal to this. Okay. So in matrix form, we can rewrite this portion as some matrix H into F. Okay, so the end effector force and the end effector moment is equal to Si Fi and Pi cross Si along Fi. So we can rewrite this in a matrix form and F into F. So what is this matrix? It is nothing but the unit vectors and the moments of the unit vectors. What is this F? That is F1, F2, F3 or the until F6. Okay, so we have the force transformation matrix. As I said, the top portion is this unit vector along the leg, and the bottom portion is the moment of that unit vector from the fixed origin. Second column is the second unit vector along the second leg and the moment of that second unit vector, and so on till the sixth unit vector along the sixth leg and the moment of that sixth unit vector. So in a Stewart-Gauss platform, there are 6 legs, and so the H matrix consists of these 6 column vectors, and it is multiplied by F, which is nothing but the F1 through F6. The prismatic joints can only apply force along that leg, along the direction of the prismatic joint. So, like the Jacobian matrix, this matrix is also not a dimensionally homogeneous matrix. Why? Because this is a unit vector, but this has some length across that unit vector. So this portion has units of length. This portion does not have any unit. Okay. But as you can see, this is so much easier to compute or so much easier to evaluate, corresponding to J, Q, transpose and the inverse of the whole thing. Okay, both must be same. Okay, in previous case also we obtained the external force in terms of the leg forces using JQ transpose inverse, and in this case it is in terms of a matrix which we call as the force transformation matrix. But this force transformation matrix is much simpler to compute, and you can easily extend to any fully in parallel manipulator. In that case there will be n columns. Okay, so now let us look at the singularity in the force domain. Okay, so what is the direct force analysis? Obtain the external forces and moment given the leg forces. So what is the leg forces? This vector F. And if we know this force transformation matrix, we can find the external forces and moments. How about inverse? Obtain the leg forces given the external forces and moment. So if I tell you that the top platform of a Stewart platform, moving platform, is experiencing some force and moment, an external force and moment is acting on the top platform, what is the forces required in the prismatic joints to keep it in equilibrium? The answer is F is H inverse into that force and moment. Okay, so there is an inverse which is coming in. If the determinant of H is equal to 0, then the inverse problem cannot be solved. That is obvious, right? So determinant of H equal to 0, I cannot find an F for the external force and moments which are acting on the top moving platform of the Stewart platform. So this is called as force singularity. Okay, so as determinant of H tends to 0, this S will tend to infinity, and any external force moment along certain directions cannot be resisted by the parallel manipulator. Okay, so analogous thing, in velocity singularity, no joint rates can cause motion along certain singular direction. Remember, theta dot goes to infinity if you want to move in the singular direction. Here, any external force moment along certain singular directions cannot be resisted by the parallel manipulator. So thing is, one is cannot be resisted, and in velocity it cannot be applied. Okay. So the force singularity can be visualized as using degeneracy of the force ellipsoid. Okay, so what is the force ellipsoid? So in a Stewart-Gauss platform, the external force is given by F, which is HF into F. So we are taking some part of the H matrix, which is the top half, S1, S2, all the way till S6 into F. So the square of this force, or the magnitude of the force, can be written as F transpose GFF, where GF is HF transpose HF. Okay, so just like we did for the velocity analysis, velocity ellipse and velocity ellipsoid. So the maximum, intermediate and minimum values of this force, magnitude of this force, subject to a constraint of the form F transpose F is equal to 1, very similar to what we did for velocity, theta dot transpose theta dot equal to 1, are the eigenvalues of GF. Okay, so since the rank of GF is 3, the tip of the force vector lies on an ellipsoid in R3. If the rank of GF is 2, the force ellipsoid shrinks to an ellipse and the Stewart platform manipulator cannot apply a force normal to the plane of the ellipse. If the rank of GF is 1, the Stewart platform manipulator cannot apply a force in a plane or cannot apply any external force respectively. If it becomes 0, then it cannot apply any external force. Okay, example. A Stewart platform with fixed base and moving platform as regular hexagon. So the top is a hexagon, regular hexagon, 6-sided equal, and the bottom is also a regular hexagon with all the 6 sides being equal. Okay, and we consider all the legs as parallel. So basically consider that hexagons are equal in size. So for such a configuration, the H matrix will be all the leg vectors along the z-axis, so 0, 0, 1, 0, 0, 1, and so on. And the moment of this z-axis can be written in terms of y and x. So b1y minus b1x, b2y minus b2x. And the z component will be 0. So there is a vertical line and there is a vector which is in the xy plane. So the moment is r cross that line. And this is what you will get. So now you can see that the 3 rows of H are 0. Okay, so 1, 2, and 3 rows of H are 0. So the HF, which is the top portion, 2 rows are 0, and the bottom portion only 1 row is 0. Okay, so GF has rank 1, obviously, right? Because there is only one column vector, so it is 0, 0, 1 everywhere. So it has rank 1. So the tip of the force vector can only lie along a line. Okay, it has dropped by rank 2 ranks. Okay, and only a vertical external force can be resisted. Isn't that obvious that you have a hexagon on top and a hexagon at bottom? All the legs are exactly vertical. Okay, so you can only apply a force from the top. Okay, and that will be resisted. Any other force in the x or y direction cannot be resisted. The Stewart platform will just fall over. Okay, so the Stewart platform in this configuration, which is the very simple configuration which you can visualize, has singularity along fx and fy. Okay, the singularity is also along mz. Why? Because you can see the last row is also 0, 0, 0. So if I apply a moment about the z-axis, again it cannot be resisted. Okay, so this kind of analysis was used in a work by one of our PhD students, and he showed how we can design a sensitive Stewart platform. Why? Because if you can make the Stewart platform very close to a singular configuration, a very small force will lead to a very large value of force in the legs. Remember, it is divided by the determinant. Okay, so he showed that you can design very sensitive 6-component force torque sensors, and these sensors are basically Stewart platform based sensors which are very close to a singular configuration, not exactly a singular configuration. Okay, finally, let's look at the relationship between gain and force singularity. Remember, in a parallel robot, we had something called as a gain singularity. And to recollect, if determinant of k star equal to 0, the parallel manipulator gains 1 or more degrees of freedom instantaneously. Okay, I have shown you for the 4 bar as well as for the 3 RPS robot. If determinant of h equal to 0, the parallel manipulator cannot resist forces or moment in 1 or more directions at that configuration. Okay, this is what I have shown in the last few slides. So the question is there a relationship between the two? Okay, what happens when you cannot resist forces, and what happens when you gain 1 or more degrees of freedom? Okay, so what I will do is I will illustrate what is happening in these two cases by using a simple 4-bar mechanism, because that can be worked out. Okay. So let's look at a 4-bar mechanism. So we have this 4-bar mechanism, and There is a force which is acting at the third joint. So this is that vector F which is acting. So when we are looking at singularity, the actuated joint is locked. So theta 1 is locked. So which means basically this point O2 is also fixed. So what do we have? We have like a truss member. We have one link, one joint, another link, and this is the fixed link. So this is drawn here in more detail. So we have a fixed base and we have a truss. We have three links and there is a force acting F, maybe at an angle beta to the horizontal axis, and then we can define these angles alpha 1 and alpha 2. So alpha 1 is this angle and alpha 2 is this angle. So this is not phi 1 or phi 2, but it is sort of related to phi 1 and phi 2. So if you have a force which is acting at an angle beta, this will lead to two forces in these two links. Let's call them T1 and T2. And the angle which these two links makes at this vertex is gamma. Okay, because of this force or because of this forces along the axial members between this link or along this link, we'll have reactions R1 and R2 at this joint. Okay, there will be a reaction at this joint also, but we can just concentrate on what is happening to R1 and R2, the reaction. So we will try to find out what is R1 and R2 as a function of F, this angle alpha, gamma, and beta. Okay, so let's repeat. With theta 1 locked, point O2 is fixed. For a given theta 1, L0 and L1, the length D opposite to theta 1 is known. Draw the planar truss structure determined by link 2, link 3 and the now fixed side O2 OR. Angles alpha 1 and alpha 2 can be computed in terms of theta 1, phi 1 and phi 2. Okay, not important, but if necessary we can find out depending on the lengths. Now consider a force Fx Fy acting at an angle at point O3, whatever I've shown you in the previous drawing. And we want to find the axial forces T1 and T2 acting along the links O2, O3 and O3, OR of the planar truss. How do we find this? We draw the free body diagram. Okay, and you can show that this Fx Fy is related to T1, T2 by this cos alpha 1 minus cos alpha 2 sin alpha 1 sin alpha 2. Okay, this is the standard problem which we do in statics in undergraduate. So there is a three link, we have a force. Only difference here is the force is not acting vertically, it is acting at some random angle, okay, beta. We can, once we have T1 and T2, okay, from this expression, we can, so once we have Fx Fy in function of T1, T2, we can also find out T1, T2 as a function of Fx and Fy. Okay, so basically what you will end up is something which is some matrix sin alpha 2 cos alpha 2 minus sin alpha 1 cos alpha 1, but there will be a division by sin alpha plus alpha 2. Okay, so from T1 we can now obtain the reactions R1 and R2 at joint O2. So let's go back and see this picture once more. So I have a force which is acting at an angle beta. These components Fx and Fy, they can be related to T1, T2 by simple force equilibrium at this node. And then from T1, I can find R1 and R2. And it turns out that you will get these angles alpha 1, alpha 2, and so on. Okay. So R1 and R2 is obtained as 1 over sine alpha 1 plus alpha 2 against some matrix which now contains both cos alpha 1, sine alpha 2 and so on into Fx Fy. So the torque required at joint 1 to keep the 4-bar mechanism in equilibrium is tau 1, which is R1 L1 S1 minus R2 L1 C1. Okay. How did I get this? This is obtained again from equilibrium. So if you look at this point, so there is R1 and R2 and tau 1 will not appear. So equilibrium at this point, moment equilibrium, will give me what is the relationship between R1, R2 and this force at, what is the torque which is acting at the joint, which is along the Z axis at that joint. Okay. So this is the expression that you will get. If determinant H is 0, i.e. if the sine alpha 1 plus alpha 2 is 0, okay, so we have alpha 1, alpha 2 and pi. Okay, so if sine alpha 1 plus alpha 2 is 0 or gamma is pi, because the sum of the three angles inside a triangle will be pi. Okay, so then link 2 and link 3 will be aligned. Okay, so think of it this way. Let's go back to this figure once more. So when determinant H is 0, sine of alpha 1 plus alpha 2 will be 0. So alpha 1 plus alpha 2 is 0. So basically this link and this link are parallel or lying on top of this base. Okay, they are aligned. So this is exactly the same as what was happening when you had gain singularity. So in the case of gain singularity with the theta 1 locked, the second link and the third link were aligned. Okay, so gain singularity is same as force singularity. So determinant of H equal to 0 is same as determinant of K star equal to 0. Okay. So gain singularity, instantaneous velocity is perpendicular to link 2 and 3. Force singularity, any force along the singular direction gives rise to infinite R1 and R2, okay, and infinite tau 1. So if you apply a force along the singular direction which is perpendicular to link 2 and 3, then you need infinite torque to keep it in equilibrium. Okay, so the bottom line is the gain singularity, which is determinant of K star equal to 0, is same as determinant of H equals to 0, which is the force singularity, at least for the planar 4-bar mechanism. Okay, and it turns out it is true for all parallel mechanisms. So in summary, statics, when we look at statics, all the actuated joints are locked and the manipulator becomes a structure. So we can find the reaction forces and moments at the joints due to externally applied force and moment using free body diagrams. Okay, we can propagation of forces and moments in serial manipulator is similar to propagation of velocities. So remember, IFI is something which is IF, some rotation matrix into I plus 1, Fi plus 1. Okay, except in a serial manipulator, it is going backwards. For velocity analysis, it went from the fixed base to the end effector. In the case of serial manipulator statics, the forces and moments go backwards from the end effector to the fixed base. So in serial manipulator, joint torques are related to external forces moments by the transpose of the manipulator Jacobian. So we have this well-known expression, tau is J transpose F. In velocity kinematics, it was V is equal to J into theta dot. For parallel manipulators, especially in parallel manipulators, we can define something called as the force transformation matrix. So the loss of rank of Jacobian or force transformation matrix is this singularity. Okay. So force moment applied along the singular direction cannot be resisted. And in gain singularity in parallel manipulator is identical to the loss of rank of force transformation matrix. Okay. So determinant of h equal to 0, which is loss of rank of force transformation matrix, is same as determinant of k star equal to 0. Okay, so with this we'll stop this discussion on velocity analysis and static analysis of serial and parallel manipulators. Thank you.